Yes, screen is visible.
Yes, sir.
Yes, sir.
Okay. Yeah. Did you study the Schrodinger equation? So that is very important one, Schrodinger wave time independent wave equation. Okay. So now we are going to the particle in a 1D box. Okay. So before going to the particle in 1D box, I will just briefly explain the once again Schrodinger time independent wave equation. Okay. So just this Schrodinger time independent wave equation is just like a Newton law in classical mechanics. Okay, by using Newton law, how we can explain the motion of the particle? Here also by using Schrodinger time independent wave equation, so we can explain the motion of a electrons, protons, that means microscopic particles. Okay, so for that just simple steps what we are taking, we will discuss here. So just we will consider the classical wave equation. What is the classical wave equation? So this is the dou square psi by dou t square equal to v square into so del square psi. Otherwise, del square psi equal to 1 by v square into dou square psi by dou t square. So this is the classical equation, wave equation. So by using classical wave equation, we are solving this here. Okay. So that's a solution is already we discussed yesterday. So just we will this is the solution of the wave equation. So we differentiate two times with respect to t. We will get some value here. So that value will substitute in the so above equation, and then we can finally we will get the so this equation. Okay. So now we are discussing here application of the Schrodinger wave equation. Application of the Schrodinger wave equation we are discussing. So that means so they will ask this question is like so particle in one dimensional box. Otherwise, just like they will ask so write the application, any application of the Schrodinger time independent wave equation. They will not ask directly. So they will ask directly. So what they will ask means so write any application, right? Any application of Schrodinger time independent wave equation. That means at that situation, this only we have to write. That means this is the application of Schrodinger time independent wave equation here. By using Schrodinger time independent wave equation, we are finding the so what is the energy state? What is the energy state of a electron? What is the energy state of a electron or proton? Anything we are finding here. Okay, so that only we are discussed here. So okay, inside the that means this is a particle. So that means this is a one box or potential well also we will call it. Okay, potential well also we will call it. So inside this potential well or inside the box, so there will be electron is moving. Otherwise inside the atom electron is moving. So what is the energy? Suppose that electron having, let us consider having a energy e. Okay, and so inside the potential, inside the box, that we have to consider so there is no potential energy, so that means we are taking here box. That means if you will take atom also, there should be some boundaries at the starting and ending. Okay, so that means at the boundary we are taking potential is infinite, potential is infinite. Okay, so that means at the starting point x is equal to 0, at x is equal to 0, that position equal to 0 position, what is we have to take? So that what we are taking one boundary, at that boundary potential equal to infinite. So another, yeah, I will make it. So and second point, at x is equal to L, at x is equal to L. So x is equal to L means that is the ending point of the box. Okay, ending point of the box. That means this is another boundary. At this boundary, so here potential also infinite. Only inside the box potential is 0. Inside the box potential is 0. So let us consider one electron is inside the box. That box have mass m. Okay, inside the box there is a potential is 0. So that in that box, so that electron is moving inside the box. So how that electron motion will be, so we have to discuss right now how that electron motion, as well as so how what is the energy of the electron we will discuss now. Okay, for that we are considering here two boundary condition. First boundary condition is equal to, so Vx is equal, Vx is nothing but here, so with respect to the position, what is the potential? So that means at x is equal 0, at x equals 0, what is the potential? So potential equals 0 here. That means Vx is equal 0. So wave function is equal to vanishes. There is no wave function. Already we know that according to the properties of the wave function at the boundaries, so wave function will be vanished. Wave function will be vanished. That means, so here, so wave function at Vx is equal to 0. So wave function equal to 0. So what is the limitations here? So that means, sorry, inside the box here Vx is equal to 0 means, so that potential is the inside the box, potential equals 0. Inside the box, potential equal to 0. So what are the limit means? So that x value will be 0 to L. X value will be 0 to L. So potential equal to 0. Potential equal to 0 at the boundaries. At the boundaries means, so that inside the box there is a wave function should be there. That means psi of x equal to not equal 0. Psi of x not equal 0. That means inside the box, so electron will be present. Electron is moving. Electron is moving means there will be a wave function. There will be a wave function. Now second boundary condition. What is the second boundary condition means? At Vx is equal to, that means here, so another condition we are taking. So what is the condition means? So if x value will be less than 0, x value will be less than 0, Vx will be infinite. Potential equal to infinite, either at the boundary or below the boundary. Below the boundary, so what is that? Vx is equal to infinite, and so wave function equal 0. And one more is here, after the boundary. After the boundary means x greater than or equal to L. So at the boundary or after the boundary, what is that? So potential equal to infinite. Potential equal to infinite. So potential equal to infinite means wave function is 0. Okay, so we are taking here two considerations. So one is, so in between the 0 to L, in between the 0 to L, so potential equals 0. That means before, on the boundary or before the boundary, so what is that? Wave function potential is infinity, wave function is 0. And at the end of the boundary, after the boundary, what is that? Wave function, the potential is infinite, wave function is 0. So these are the conditions we are taking here. Okay, yes. Now for explaining the motion of that particle, for explaining the motion of that particle, so we are considering here Schrodinger time independent wave equation. Schrodinger time independent wave equation. Already we know that. What is the Schrodinger time independent wave equation? Dou square psi by dou x square, dou square psi by dou x square plus 2m by h cross square. H cross means here h by 2 pi, h by 2 pi. So that means here for remembering, we are simply, we will take here 2m by h square. Okay. So if you substitute instead of h cross means h by 2 pi means that equation will be 8 pi square m by h square. Okay. Into e minus v psi is equal to 0. Okay. So now inside the box, the potential equal to 0. Inside the box, so what we are taking here? Potential equals 0. So that's why substitute here v is equal to 0. Therefore, so dou square psi by dou x square plus 2m by h square h cross square into e psi is equal to 0. So let us take this is equation 2. Okay, so that means here what we are taking, just potential v is equal to 0 we are taking, because inside the box, so there is no potential. There is no potential. Okay, so let us take this total term 2me by h cross square equal to k square. 2me by h cross square equal to k square. Okay, so now this total is constant because m is constant, h cross is constant. So if you will take particular energy, if you will take particular energy, so that energy equal to, here we are taking constant. That's why, so this total we are taking another constant that equal to k square. K square. Okay, so here energy is depends on state. We don't know, so that electron is in which state. So that's why initially we are taking here, so constant. Okay, that's why, so 2me by h cross square equal to k square we are taking. Okay, now, so this is the one differential equation. Yeah, one more minute. Yeah, so this is the one differential equation. Okay, so now where k square equal 2me by h cross square. Okay, now solution of this differential equation. Now solution of this differential equation here. So what is the solution means? Psi of x is equal to a sin kx plus b cos kx. B cos kx. Here k is the constant. Whatever we are taking here, that constant. X is the position of the electron. X is the position of the electron. Okay. So now, so what is the solution of this equation means? Psi of x is equal to a sin kx plus b cos kx. Okay. Here a comma b are the constants. Okay. So already we know that what is the k? K is the this one. Now coming to the, yeah. So to calculate the above equation, we have to consider two boundary conditions here. Two boundary conditions, whatever we discussed previously. Okay, so whatever we discussed previously, that condition only we are taking here. So first boundary condition equal to, so what is the first boundary condition means? So there are two boundaries are there. At x is equal to 0, one boundary. At x is equal to L, another boundary is there. Okay, already we know that at x is equal to 0, wave function equals 0. At x is equal to 0, wave function equals 0. That is the first boundary condition. Similarly, second boundary condition. At x is equal to L. So in that at x equal to L also, so wave function, what is that wave function? So at x equal to L also potential is infinite. So that's why, so electron doesn't exist. So that's why wave function is 0. If wave function is 0. So by using these two boundary conditions, we will solve the above equation. We are taking here solution. So this is the solution. Let us take that is equation 3. Okay. So now applying the first boundary condition for equation 1. Okay. So if you so that means at x is equal to 0. Substitute instead of, so at the point at the presence of x, substitute 0 value. Okay. So here sin kx is there. So instead of x we are substituting 0 here. So similarly here cos kx is there. Instead of x we are substituting 0. Okay. That means it will become sin 0 and cos 0. And if you substitute x equals 0, what is the wave function? Psi of x equals 0 na? Psi of x is equal to 0. So that's why 0 is equal to a sin 0 plus p cos 0. Okay. So but here, so we know that sin 0 value is equal to 0. So that's why this term will be vanishes. This term will be vanishes. Okay. So what is the remaining term? B cos 0. Cos 0 equal to 1. That means from this equation cos 0 equal to 1 means, so this value will become 1. So B is equal to 0. From this equation, what we will get? So here this term will be vanishes. So that's why, so only this term will be present. This term is equal to 0. But in this term, cos 0 value equal to 1. So therefore, so B is equal to 0 we can write. B equal to 0 we can write. So from the first boundary condition, what we have calculated here, B is equal to 0. Substitute this value in equation 3. What is this equation 3? This is the equation 3. Substitute the B value in this equation 3. Okay. So here if you substitute B equal to 0 means what is the remaining term? Psi of x is equal to a sin kx. Psi of x is equal to a sin kx. Okay. Now, so remaining equation, if you substitute the B value 0 means in equation 3, what is the remaining equation? Psi of x is equal to a sin kx. Let us take this is equation number 4. Equation number 4. Now apply the second boundary condition. Second boundary condition for equation number 4. Okay. According to second boundary condition, so what is that? X is equal to L. At x is equal to L. Substitute the x equal to L value. So what is the psi of x? Psi of x will become 0. Okay. A sin KL is equal to 0. If you apply the second boundary condition, so what it will become? Equation 4 will become, so a sin KL equal to 0. Okay, so here a sin KL equals 0. So that means from this equation, what we can write means, so we cannot write a equal 0. Okay, so that means that equal constant. That value is equal constant. So that's why this function should be 0. This function should be here 0. Okay, consider particle is present in the box and it cannot be come out from the box because the potential is infinite outside the box. Therefore, a cannot be 0. A cannot be 0. Hence, so only, so this equation, this total term is 0. This total term is 0 means either A cannot be 0. So that's why sin KL should be 0. Sin KL should be 0. Okay, therefore we are taking here sin KL equal to 0. Sin KL equal to 0. Okay, so from this, at which situation sin KL will become 0? At which situation sin value will become 0? Okay, suppose sine theta, when it will be 0, either theta is equal to integral multiple of pi. That means here n equal n pi. So either so that means yeah, theta is equal to 180, theta is equal to 0, theta is equal to 360. At these values, what happened? Sine theta will become 0. Sine theta will become 0. So that's why what we are taking means sine kl equal to, at which values sine theta will become 0 means sine n pi values. Here n equal to 0, 1, 2, 3, so on. 0, 1, 2, 3, so on. If you will substitute sine n equals 0, so that means sine 0 equals 0. Sine if n equal to 1, sine pi value also 0. So that means if you will take like this formula instead sine n pi, okay, so then so for that all terms sine kl will become 0. Okay, so that's why here, so that means sine kl equals sine n pi we can write. Okay, so therefore so kl equal to n pi, so k is equal to n pi by l, k is equal to n pi by l. Let us take this is equation number 5. So okay, so from this we are calculating here. Already we know that so previously we are taking here k square is equal to 2me by h cross square. K square equal to so 2me by h cross square. Previously we consider that this total equal to constant, that constant equal to k square, but according to so our solution k is equal to n pi by l, k equal to n pi by l. So now k square it, so square it both sides, k square equal to n square pi square by l square. Okay, equate this and this both equations. Okay, so now so 2me by h cross square equal to n square pi square by l square, n square pi square by l square. Okay, if you solve this equation, from this equation what we have to do means we have to calculate the energy value. So from this E is equal to, so bring remaining all terms this side. Okay, n square pi square by l square is same, and so h square it is in denominator. If it will come this side means what it will become, it will become into the numerator. Okay, h square by 2m, okay, so this is the energy here. Okay, if you simplify this equation, but we know that h cross equal to h by 2 pi, h cross is equal to h by 2 pi. We are substituting that value here, so that means h square by 4 pi square, this 2m is common. Okay, if you simplify this equation, energy value you will get n square pi square by 8m l square, 8m l square. Okay, so if you don't substitute, that means directly we can calculate, so n square h cross square by 2m l square, 2m l square. So what is the difference mean? Just we are substituting here h cross by 2 pi in this equation. So therefore energy equal to n square pi square by 2m l square. Okay, here h also there, n square pi square h square by 8m l square here, n square pi square h square by 8m l square. Okay, this is the energy value here, Okay, so by using Schrodinger wave equation, what we are calculating, energy of the electron, Okay, I will explain you here. So for n equal to 1, so what is that? E1 is equal to pi square h cross square by 2m a square. Okay, so for n equal to 0, what is that? Energy value E is equal to 0. So that means that is we will call it as ground state. So for n equal to 1, so E1 is equal to so pi square h square by 2m a square, So this is first excited state at 0 point energy. Okay, so now for n equal to 2, so E2 is equal to, here that means total remaining all are constant, just we are substituting here n square pi square h square by 2m a square. So instead of n square, what we are taking 2, so that means n square equal to 4 into pi square h square by 2m a square. Okay, so this total value equal to E1, 4E1. If you will take E2 is equal to 4E1. Similarly, E3 is equal to 9E1. So similarly, we can write En is equal to En. That means if you want nth state, what is the energy means? N square into E1. So this shows that the energy of the particle in one-dimensional box. See here. Okay. So if E is, that means what is the energy? If n equal to 1, if n equal to 1 means so this energy will be like this E1. That means electron should be here. If n equal to 2, electron should be here. So if n equal to 3, electron should be here. So their energy will equal to 4E1. So here if n equal to 3, electron will be in third state means their energy will be 9E1. If electron will be in fourth state means that energy will be 16 into E1, like that, so on. Okay, so like that we can calculate the energy of the particle. Energy of the particle. So energy of the particle. So by using Schrodinger wave equation. So this is the energy levels or eigenvalues. So these are the energy values or eigenvalues. So sometimes they will ask the eigenvalues of particle in 1D box. Eigenvalues of particle in 1D box. So what is the eigenvalues mean? Just energy values. What is the energy values will be there? So those values we will call it as eigenvalues. Okay. Now coming to the wave function. Wave function. So previously what we have calculated here. So by using this equation we have to calculate. So there is two functions. First one is the energy. Second one is the wave function. Second one is the wave function. What is the wave function of the electron? So here energy we are calculated. So that energy is so distributed like this. So energy is distributed like this here. Okay. So now we will calculate the how wave function will be present. How wave function will be present. Okay. According to the, so what is that we are calculated? Psi of x is equal to a sine kx. So from that equation 4. So there is a equation 4 will be there. So from that equation 4, psi of x is equal to a sine kx. So what is the k value here? K is equal to n pi by L. K is equal to n pi by L. If you substitute the k value, so then we will get psi of x is equal to a sine n pi x by L. So this is, let us take, this is equation number 6. So now we have to calculate that this is the wave function here, but a is equal to constant. We have to calculate the a value. What is the a value? We have to calculate it. So for calculating the a value, we have to normalize it. We have to normalize it. So normalizing means, so for finding the total probability. What is the total probability formula? So integration of psi star into dx. Psi star into dx is equal to 1. Psi star into dx is equal to 1. Otherwise, instead of psi star, so what we are taking here? So det psi square. Okay. So what is the difference between psi star? Means psi star, I explained you. Psi star is complex conjugate of the wave function. So that means this is psi of x. Okay, so that means here, suppose in this wave function there will be imaginary part will be there. Imaginary part, suppose a sine ikx, will be there. So if you will take complex conjugate, means instead of I will write minus I. If you will take, suppose if it will be constant, that means if there is no I value, means so that the complex conjugate value doesn't change. If imaginary part will be there, then only complex conjugate value will be changes. So that means, suppose here sine ikx will be there, means instead of I, so if psi x is equal to a sine ikx, psi star x is equal to, means instead of I, what we are writing, minus I. Okay, but in this case there is no imaginary value in the psi of x. So that's why, so complex psi value will be same, complex conjugate value of the psi also same. So that means we can take det psi of x square dx. Okay, so this is the total probability of finding the particle. Total probability of finding the particle inside the box. So this also called as normalization condition. Okay, so that means if you substitute the psi of x value in this equation. Okay, so what we will get? So what is the limits here? Why we are taking 0 to L means, so lower limit is 0, so upper limit is L. After, so that means in this limit only electron will be exist. That means within the particle only electron will be exist. So beyond the boundary there is no particle. After the boundary there is no particle. So that's why we are taking only limits here 0 to L. So now we are substituting the psi of x value in this equation, normalization equation. So if you substitute the psi of x value, so what we will get here? A square sine square n pi x by L into dx equal to 1. Okay, so here a square equal constant, we can kept outside. So and remaining term is sine square n pi x by L into dx is equal to 1. So that means this sine square x we can write into 2 cos x by 2. Okay, 2 cos x by 2. Okay, so 2 cos 2, yeah, so 2 cos, so 1 by 2 I am taking common here. Okay, so that means so we can write sine square equal x is equal to 1 minus 2 cos x here, 1 minus 2 cos x. Okay, so 1 by 2 is we are taking common out, that's why 1 minus cos x by 2, 1 minus cos x by 2. So sine square x how we can write means, so how we can write means 1 minus cos 2x we can write, 1 minus cos 2x we can write. Okay, so I am writing same like that only here. So just what I do means 1 by 2 I am taking common out. Okay, now so apply the integration for this total term. Okay, so if integration of 1 dx, integration of 1 dx that equal to x, that equal to x. So integration of cos x, integration of cos x is equal to sine x. So what is that sine here, something, some constant into x will be there. Okay, sine x, sine ax by a we can write now, sine ax by a. Okay, so that means here 1 by 2 is common. So here a square by 2 will be there. A square by 2 will be there. Okay, x into this total term. So sine cos 2x integration will be sine 2x by some constant sine kx by, so k, some sine kx by k. Here some k value will be 2 n pi by L. Okay, so if you substitute the limits, if you substitute the limits here, see here, so the sine value equal to integral multiple of 2n. That means 2n means here that will be, that value will be always even number, always even number. Okay, so 2n pi, 2n pi means either 0, 360 or 180. So like that only. Okay, so like that only. So that's why for those values, for those values what happened, sine theta will become 0, sine theta will become 0 after substituting the limits also. So what happened, so for all both limits, 0 limit and L limit, what happened, this total term will become 0. So, okay, now so only one term will be there, so that equal to x. So if you substitute the boundary conditions here, upper boundary minus lower boundary, upper boundary is L, L minus 0. So this total term will become 0. So a square by 2 into L minus 0, that equal to 1. So a square L by 2 is equal to 1. So here a is equal to under root of 2 by L. A equal to under root of 2 by L. So this is the a value. Substitute this a value in equation number 6. Okay, so what we will get, psi of x is equal to under root of 2 by L into sine n pi x by L. Okay, sine n pi x by L. This is the wave equation. This is the wave equation of the electron. Okay, this is the wave equation of the electron. According to that, see here, suppose if psi is so this is the lower boundary, this is the upper boundary. If yeah, actually this is the psi 1, this is psi 2, this is psi 3. Here mention is wrong. So this is n1, this is n2, this is n3. Okay, so if n equal to 1, if n equal to 1, psi that means psi of 1 equal to, wave will be like this, wave will be like this. See here, so we are calculating psi of x is equal to under root of, so sine n pi x by L. Instead of n we are taking here, so 1, 2, 3, so on. Okay, if you substitute n equal to 1, n equal to 1 means, so what we are getting here, so this is n equal to 1, n equal to 1. So here mention is wrong here. So this is psi 1, psi 1 equal to, so if you substitute n equal to 1, so that wave will become like this, wave will become like this. If n equal to 2, wave will become, this is the psi 2, wave will become like this. If n equal to 3, so wave will become like this, wave will become like this. Okay, now so probability, so probability of the finding of the particle. Okay, probability of the finding of the particle means, so what is the formula, so p is equal to, so psi square dx, what is the formula here, so probability of finding the particle equal psi star, that means psi square. Psi square means already we know that psi value, so under root of 2 by L or a, 2 by a into sine square n pi by n pi x by L here. Okay, if you substitute that, that means according to this formula we can calculate the probability also. So probability, so for n equal to 1, this is the probability of finding the particle. For n equal to, this is the probability. Okay, so for n equal 3, this is the probability of finding the particle. Okay, so now like that, so we can calculate the probability of the finding the particle also. Okay, so here n equal to 1. So what is the maximum x value? X means length of the box. Length of the box is equal to, so x is equal to a by 2. A by 2. Okay, for n equal to 2. So most probable position for finding the particle. Yeah, so for n equal to 1, if you will take n equal to 1, so where we can find the particle? Where we can find the particle means x is equal to a by 2. X is equal to a by 2. So what is the most finding the probability of the particle? So here it will be maximum. That means wave function will be maximum here. Wave function will be maximum here. So that's why. So where is the probability of finding the particle? Electron, where electron will be present. So that means at this position we can find the particle. So that means not total finding the particle. So maximum probability. Maximum probability will be x is equal to a by 2. Similarly, for n equal to, for n equal to where we can find the particle means, so where is the maximum probability? Where is the maximum probability of finding the particle? So where is the maximum probability of finding the particle means at x is equal to a by 4. Similarly, x at x is equal to 3a by 4. 3a by 4. Similarly, so if n equal 3, so what is the maximum probability of finding the particle means at a by 6, 3a by 6, and 5a by 6. 5a by 6. So that means depends on like this, a by 6, 3a by 6, 5a by 6. So like this we can calculate the probability of finding the particle. Okay, so that means by using here Schrodinger wave function, by using, so that means by using this formula. So n equal to 1. So what is that here? N equal to, see here, 1 minute. Yeah, so n pi x by l, n pi x by l. For n equal to 1, what is that? So pi x by l. Okay, so see here. Yeah, so n, so this is here, instead of l we are taking a here. So n pi x by n pi by l into x. This is, if you will take n equal to 1 means, so this will be pi by 2. If you will take n equal to 2 means this will be 2 pi by 2, like that. So that means from this condition, if you equate this condition, so we can get x is equal to a by 2n, 3a by 2n, 5a by 2n, like that. Okay, so based on that, so we can calculate here. So what is the probability of finding the particle? So maximum probability we can find. Okay, so this is the probability of finding the particle. Okay, same like that only. Now we are taking here, once again I will explain you. Okay, so already we know that what is the boundary conditions we are taking only. So that means there is, first we are taking two conditions. What is that? So according to first condition, so the particle will be only present inside the box. That's why wave function does not 0. Okay, so that means inside the box potential equals 0. Potential equals 0. So according to second condition, so that means so what is that? If x is equal to less than 0, less than or equal to 0, so what happen? Wave function will be, wave function will be not equal to 0. Wave function equals 0. So potential is infinite. Potential is infinite. So at x greater than or equal to L, at x greater than or equal to L, wave function will be infinite. Potential will be infinite. Wave function will become 0. Wave function will become 0. So that means when wave function will become 0 means, so if potential will become infinite, so electron does not present. Electron does not present. That's why we are taking here wave function will become 0. So at this boundary and so this boundary, before the boundary or after the boundary. Okay. Now, so for the solution according to the Schrodinger time independent wave equation. So this is the Schrodinger time independent wave equation. We are applied particle inside the box. Inside the box means, so potential is 0. Potential is 0. So the equation will become like this. Okay, solution. So that means this total term we are taking here constant, that equal k square. Okay, so that solution of this equation. Solution of this equation equals psi of x into a sin kx plus b cos kx. Okay, so for solving that above equation, we are taking two boundary condition. So already we discussed at x equals 0, wave function will become 0. That is the first boundary condition. So second one is at x equal to L, so wave function will become 0. That is second boundary condition. Okay, now if by using first boundary condition, if you solve this equation means, so at x equals 0, so substitute x equals 0. Okay, so psi of x will become 0, so that means sine 0 will be 0, this term will be vanishes. So now b cos 0 equal to 0. So from this, so cos 0 equal to 1, so therefore b is equal to 0. We are calculating the b value here. Substitute this b value in equation number 2. Okay, so what we are getting here, psi of x is equal to a sin kx. So this is the wave function here. We have to calculate the k value as well as a value. Okay, a is the constant and k is the constant. Okay, for that, so what we are doing means we are applying the second boundary condition. So what is the second boundary condition? At x equal to L, wave function will become 0. So instead of x, we are substituting L here. Okay, therefore sin a sin kl equal to 0. So from this here, we are calculating, so sin kl equals 0. Sin kl equals 0. When sin kl will become 0 means at sin n pi value. Sin n pi values, so this will become 0. Okay, that's why we are equating sin kl equals sin n pi. So therefore kl equal to n pi. K is equal to n pi by L. So this n pi value substitute in the above. So that means this equation, equation 4. Okay, therefore we can get psi equal to a sin kx. A sin n pi by L into x. Okay, so now from this n pi value, already we know that k is equal to, so first we are calculating the energy. First we are calculating the energy, then we will go for the wave function. So in the exam, if they ask particularly, only calculate the eigenvalues or energy means we will calculate only energy values. So if they ask only wave function means we calculate only wave function. So if they ask both, only you didn't mention means you have to calculate both. You didn't mention anything means you have to calculate, so energy eigenvalues, that means energy values as well as wave function. Okay, now coming to the, so already we know that k, so k is equal to n pi by L. Already we know that k square. Okay, so if you equate that, so we can get the energy value. So here depends on the n value, there are so many number of energy states. Okay, if n equal to 1, so this is the one energy state, n equal to 2, so this is the energy state. So depends on that, so there are so many energy values will be there. So these energy values we can also call it as eigen values. Okay, now similarly, so this is the wave function. Okay, in that wave function, what we are calculated here, a value we have to calculate. For that we have to, what we have to do means we have to do the, so we have to take the normalization condition. So just substitute the psi value in that normalization condition, we will get the, if you solve it, we can get the a value. A is equal to under root of 2 by L. So just substitute that a value in the above equation. This is the wave function. If you substitute different n values, we can get the different wave function. Psi 1 is equal to psi 1 equal to under root of 2 by L into n pi by x. Okay, so that is the pi by x into like that. Okay, pi by L into x. So that is the psi 1. So similarly, n equal 2. So we will get second value. So n equal 3. So we will get the third wave function. Okay, for different values, wave function will be like this. Okay, similarly, probability of finding the particle. Also, so it will be different for different values. If n equal to 1, so that will be probability will be like this. So n equal to, that probability will be like this. Okay, so this is the maximum probability of finding the particle. Okay, so for n equal to, there are two maximum probabilities. For n equal to 3, there are three maximum probabilities. Okay, so this is the particle in one-dimensional box. Okay, particle in one-dimensional box. Okay, yeah, so I think everyone understood this. Is there any doubt? If anyone have any doubts means you can ask. I will take the attendance here.
No, sir.
Okay, so 1 minute I will take the attendance. After attendance you can leave. Okay, so here. Yes, M4. Why are you doing nonsenses? Okay, you can leave. Every time, yeah, every time
Bye,
M4.
sir. Thank you,
Yes,
sir.
yes. Okay, bye. If you have any doubts means you can ask. Okay.